All right, so in this video, I'm going to talk about a two-asset portfolio example of risk and return and kind of what happens with that and how that affects the risk profile of the portfolio and so forth. So if I had a portfolio of just two assets, so I'm going to call those assets asset A and asset B. The expected return of the portfolio would be the weight or the proportion of my money invested in asset A times the return I expect to get for asset A plus the weight or proportion of my money invested in investment B times the return I am expecting for investment B. Now, keep in mind, if you go back to the return video that I posted, the return I'm expecting for A is based upon sort of a probabilistic assessment of different possible outcomes, and that would be true for B as well. So those are sort of expected returns for the different assets, but they're not guaranteed, at least not in most cases. So the weight of A is going to be the proportion of my money invested in A. The weight of B is the proportion of my money invested in B. And because my portfolio only has the two assets, then basically what that means is those two weights are going to have to add up to 1 because 100% of the portfolio is invested in either A or B. So 1 equals WA plus WB then. Now, what that means then is basically the expected portfolio return is basically just a weighted average of the expected returns of the two assets. So basically, just do a weighted average. It's weighted by the proportion of my money in the different assets. So it's just a weighted average of the expected returns of the two assets. So that's pretty straightforward. So the return is expected return is pretty easy. Where things get more interesting is when you start looking at the risk associated with the two asset portfolio. So let's take a look at that. So I'm looking at the risk of the two asset portfolio. The expected portfolio variance for a portfolio of two assets, A and B, you go back to the risk video that I posted, basically, and I start substituting into that formula. What I'm going to get is the variance of the portfolio or expected portfolio variance is going to be the weight of the first asset squared times the standard deviation squared. So this is the variance then. So the weight of A squared times the variance of A plus the weight of B times the variance of B. And then I would actually have two terms that are WA, so the weight of A times the weight of B times the covariance between A and B. And what that came from was when looking at that formula to calculate the variance of the portfolio, we had the covariance between I and J, and I and J were denoting the two assets. So you look at the covariance of the returns from A and B. So you had covariance of returns of A with B, and then the covariance of B with A. And so when you looked at that, you'd have two different covariances, covariance with A and B, covariance of B with A. Well, the covariance of A with B is the same thing as the covariance of B with A. But when you go through that formula, you would get both of those terms, A with B and B with A. And so that's why we would have two of these terms here. So I'd have 2 times the weight of A times the weight of B, the covariance of returns of A and B. All right, well, based on what I talked about in that risk video, the covariance of A with B, I can substitute that the standard deviation of A times the standard deviation of B times the correlation coefficient between A and B. So in that case, I'm now going to look at sort of two possible extreme situations. First, if the correlation is 1, and then next, if the correlation coefficient is -1. So a correlation coefficient of 1 means that basically they are perfectly positively correlated. So if it's perfectly positively correlated, then I just substitute a 1 in here for this row AB, Greek letter row AB. So I substitute a 1 in there. When I do that, I get this term down here. And if after staring at that term for a little bit and digging back into the recesses of memory from high school algebra, but you realize you can factor that out into this squared. So basically, when you look at that, this means that the variance of the portfolio is basically the weight of A times the standard deviation of A plus the weight of B times the standard deviation of B. And you take that whole term in brackets and square it. That's what you get. So basically, the portfolio variance winds up being, I take a weighted average of the two asset standard deviations, square it, and there we go. So kind of it's kind of a weighted average of what's coming from those asset variances, those standard deviations in the formula here. Now, if I look at the other extreme, so the first case was if they were perfectly positively correlated. So when two assets are perfectly positively correlated, when one is going up, the other is going up. And when one is going down, the other is going down, right? So they're perfectly positively correlated. If they're now perfectly negatively correlated, that means when one asset is going up, the other asset's going down. And when this asset is now going up, then this one is now going down. So they're going in the exactly opposite directions. So if it's perfectly negatively correlated, I substitute this rho AB of -1 into this formula here. And that gives me a negative sign in front. So that's what I have down here. So my portfolio variance is going to be the weight of A squared times the variance of A, plus the weight of B squared times the variance of B, because sigma squared B is the variance of B, minus 2 WA, WB, sigma A, sigma B. And so I've got this minus sign over here. Well, if you, again, dig back into the recesses of memory and work out the math using high school algebra, what you find is that I could actually factor this out and show that the variance, sigma squared, of the portfolio is going to be equal to WA, sigma A, minus WB, sigma B, that whole quantity squared. Now, the reason why that's kind of important, if you remember from the prior slide that I had up here, WA and WB sum to 1. So I can rearrange that a little bit and basically show that I could substitute for WB 1 minus WA. I can substitute for that. And basically I'd have WA sigma A minus, then I'd have 1 minus WA times sigma B. And if you start looking at that, basically what you realize is there's some combination or some weight that I could plug into that. It would actually make this term and this term cancel out. Because I've got a minus sign in here and I'm subtracting this standard deviation term from that standard deviation, weighted standard deviation term. So if all I have to do is just find just the right weight of A, or which would basically mean just the right weight of B, and I can make that whole term in brackets turn into a big 0. Okay, so if I have two assets that have a perfect negative correlation, so the correlation is -1, there's some combination of asset A and asset B that would actually have 0 variance, so no variance whatsoever. Okay, now let's take a look at what that would look like on a graph. Okay, so if I look at risk and return for the two asset case, I've got risk down on the x-axis, I've got return on the y-axis. So basically, if I start off with a portfolio of just investment A, I'm over here at this point, and I've just an investment B, I would be just at this point. If I have some combination, the return basically says, as I shift my portfolio from A to B, I just do a weighted average. So I would just shift my return along that line from A to B. So my return is just moving evenly between A and B as I shift from asset A to an asset B. So if I'm 100% asset A and I go to 100% asset B, my return just moves nice and neatly along this line. But what is important to note is what happens to risk depends on what those correlations are. So if my correlation, my rho, is equal to 1, then basically what happens is as I move from having a portfolio of just A to just B, I would basically track along this line here. What that would mean is since they are perfectly positively correlated, my returns are basically, I just smoothly transition in return, and I smoothly transition in risk, and basically I just wind up on a straight line between those 2 points. So if they're perfectly positively correlated, I can decide where along the line I want to be, but ultimately it's just kind of a weighted average in terms of return and a weighted average in terms of risk, and I wind up basically just somewhere along this line. Where things get really interesting is if they are perfectly negatively correlated. So as I discussed on that prior slide, if they're perfectly negatively correlated, there is some combination of asset A and asset B that would have no risk whatsoever. So what that means is there's some mixture of A and B that would wind up over here with no risk. And so my returns are just going to move evenly from the returns from A to B when I just change the mixture of my portfolio. But the return actually shifts all the way back to 0 at some point if they're perfectly negatively correlated. So if the assets are perfectly negatively correlated, I'm either somewhere along this line or somewhere along this line. Okay. And there's some spot at which some combination of A and B that has no risk whatsoever. And I've tagged that as the risk-free rate. because it has no risk. So it would be the rate of return I would expect to get on a risk-free investment. Okay. Now, most assets that you look at out there, so I think most stocks I can put together. So let's say I have a 10 stock portfolio or something like that. Most stocks that I could put together are not going to have a perfect positive correlation. They could be pretty high, not going to be perfectly positive, but they're also generally not going to be perfectly negative either. So most of the time, what you're going to find is some kind of weakly positive or perhaps somewhat more strongly positive, but some kind of a positive correlation, which is not a perfect one correlation. And so what's going to happen for that is the different types of correlations will actually lead to kind of these curves that are bounded in this triangle. So these curves kind of start showing up. So the more perfectly positively correlated the two investments are, the closer it is to this straight line over here. But as I move from, say, a correlation of 1 to maybe, say, 0.8 or something like that, I start getting more of a shape that looks like this. And then if I drop it even further, I might get a shape that looks more like that. And if I keep going further and further until I start getting all the way to a negative correlation, then I wind up all the way over on this set of straight lines. So what that means is most assets are some level of positively correlated, but not perfectly positively correlated. So for most investments, if I had two assets, A and B, if they're not perfectly positively correlated, they're also not perfectly negatively correlated. If I plotted the risks and returns for different combinations of A and B, what I would get would be something on a line that might look something kind of like this. And so basically, from looking at that kind of curve, why do we care about that? Well, here's why we care about that. Notice that the return, again, is just, I'm just doing a weighted average of return, but notice this spot right here. So this spot right here basically means I could do some combination of A and B that is actually, the portfolio would be less risky than A, and it would be less risky than B. So there'd be some combination that actually has less risk than the two component pieces, which is why in finance, we love portfolios. Because in a portfolio, it's possible to create a combination, as long as everything's not perfectly positively correlated, it's possible to create a combination that actually has less risk than any of the component pieces that I have. So that's a possibility. I could actually create a portfolio that is less risky than the individual underlying pieces, basically because I wind up with those correlations causing the graph to have this kind of this curve shape here. And I can wind up somewhere on that curve that has actually less risk than the underlying individual investments. Now, this is just showing the two asset case because it's a lot easier to try to graph just two assets and what that would look like. But the basic idea is the same if you're looking at a 100 asset portfolio and so forth. What can happen is basically you can get a combination of investments that is actually less risky than the underlying pieces within the combination, basically because the individual investments are not perfectly positively correlated. So as long as they're not perfectly positively correlated, that combination can actually be less risky. And that's actually why we love portfolios of investments in finance. Hopefully this video has been helpful. Thank you so much for watching and have a great day.